we're going to begin with something that is the source of everything we're going to talk about in the entire class, and that is charge. I like to give simple, plain-spoken definitions of things. So charge, we'll say, is a property of matter that creates force. A property of matter that creates force. Even the initial concept of charge can get confusing because we have to jump between charge at the microscopic scale, the scale of atoms and molecules, to charge at the macroscopic scale, the charge of you and me and chalk. Okay? So since that gets confusing, I like to start by describing it in both worlds. Okay? So we're going to start with microcharge. So to see where a charge is at the microscopic scale, you have to draw something that you've probably seen before. N, P, 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 and then like that, with an E out here, and an E out here, and an E out here. So you've probably seen this before. If you're from the 50s, you might be cowering under your desk. This is an atom. Okay? This actually is specific atom. This is lithium. Because you keep up with elements based on their atomic number, based on how many protons in the nucleus. So 3 protons, it must be lithium. Lithium, very cool element. It was used, it makes grease, and it makes you feel better, and it makes nuclear weapons, and Nirvana wrote a song about it. So there's the 4 things I know about lithium. That's all I got. So now let's look inside this lithium atom and see where the charge resides. Well, it's in these subatomic particles. So we can look at the proton and ask ourselves, what is its charge? Charge of a proton is plus 1e, where E is the unit. E means elementary charge unit. It's defined as the charge of a proton. So this is 1.00, as many zeros as you want. The charge of a proton is exactly 1e. There's also, in the nucleus, there's the neutrons. And the charge of a neutron is 0. The neutrons are neutral. 0e. And then flying around the outside are the electrons. And electrons are negative. So its charge is minus 1e. Same amount of charge as a proton, just the opposite sign. One thing to stress is that E does not mean electron. Sometimes people see that E and they think, oh, that must be a negative charge. The unit must be negative. It must mean electron. It doesn't mean electron. Often we draw little e's to mean electrons. Sometimes we write an E and we mean this particle an electron. Sometimes we put a negative sign on it to clarify that it's an electron. But when you see it next to a number, you have to use your context and realize that doesn't mean electron. That means elementary charge unit. And it is not negative. It is also not positive. It's just a unit. Units don't have signs. The sign comes from the number in front of it. Okay? So if you see a number in front of an E, if it's a plus, then you know it's positive. If you see nothing, we assume nothing means a positive number, so that's also plus 1e. But if it's negative, we'll put a negative in front of it. Okay? But E is not negative. E is elementary charge unit. We can think about the difference between the microscopic and the macroscopic scales by also giving you the charges in terms of the macroscopic unit of charge, which is the coulomb. So the charge of a proton in coulombs is 1.6 times 10 to the minus 19 C for coulomb. The charge of the neutron is 0 C. Regardless of the unit, it is 0. And the charge of the electron is the same, it's just negative, minus 1.6 times 10 to the minus 19 coulombs. So a big jump between the microscopic and the macroscopic worlds. We can also, while we're thinking about it, look at the mass. We can also see the jump or the difference in the mass. Mass also has a microscopic unit, U. So the proton's mass is 1.007 U, where U is the unified atomic mass unit. The neutron has a very similar mass, sitting here in the nucleus with the proton, 1.009 U. And in the electron, we think of the atom is having a heavy nucleus with light electrons sort of flying around in orbits. And sure enough, the electron's mass is very small, 0.0005 U. If we want, we can think about the macroscopic scale, and we can write these numbers in terms of kilograms. And let's do it. So the proton mass is then 1.67 times 10 to the minus 27 kilograms. So an even bigger difference than in the charge, 27 orders of magnitude in the mass. The neutron, I'm going to write with the same number, 1.67 times 10 to the minus 27 kilograms. And I'm writing the same number because here I kept up with it to 4 places, and here only 3. So pretty much if you're keeping up to things with sort of 1%, and our homework is only within plus or minus 5%, then these are essentially the same. Right? This is a very small difference. And if you are really keeping up with things only to about this level, the electron mass comes out very small, 0.0009 times 10 to the minus 27 kilograms. So again, if you're just keeping up with it to sort of this level, you can pretend the electrons weigh nothing. Right? If you're just estimating based on the mass of something how many electrons and protons and neutrons it has, you can pretty much ignore the electrons. They don't weigh very much. And they're similar in number to the other particles. Okay? So now let's think about how these things get charged up. Here's a closer look at that lithium atom. Let's see, it had 3 protons and 4 neutrons, and it had 3 electrons flying around. And if we're going to talk about charge, we need to figure out what is the total charge. Well, it obeys superposition, which is just a fancy physics way of saying add it all together. Right? So the total charge really is just the sum of all positive and negative charge. So if I wanted to know the total charge on this atom, I would just say, well, it's 3 protons, so 3 times plus 1 E plus 4 neutrons times, oh, but 0 E plus 3 electrons, 3 times minus 1 E. And I would add it up together. That's 3E plus 0 minus 3E equals 0. So sure enough, the charge on an atom in its natural neutral state is 0. It's neutral, just like it should be, right? Just by adding up the charge. Right? The math will get harder, I promise. Now, we want to think about something that's not neutral, that has charge. Something bad has to happen to this lithium atom. Something horrible. Let's say it is to lose an electron. I don't know how. I don't even want to ask. Who knows? Let's just say it loses an electron. P, 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 N, 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 E, E, and that's all. It looks horrible. Well, let's add it up real quick. 3 times plus 1 E plus 4 still times 0 E plus only 2 times minus 1 E. Now, of course, we don't have enough negative charge to balance the positive charge, so we end up with something that is charged plus 1 E, plus 1. So it's a lithium ion. And its charge is plus 1 E because it's missing one of its electrons. You can have a lot of different kinds of ions. You don't just have to lose an electron. Maybe something really weird could happen. You could gain 2 electrons, say. Oh my goodness. P, 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 N, 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 E, 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 E. Now it's a mess of electrons. And we could add it up. 3, 3 times plus 1e plus 4 times 0e plus, now we gained 2 electrons, that took us up to 5, plus 5 times minus 2e. And we'll get, I'm sorry, 5 times minus 1e. And we'll get a charge that's negative. We'll get minus 2e for the total charge. So you can see this is really just trivial addition. This would be a lithium ion, and usually it'd be written like this, lithium, chemical symbol for lithium, 2 minus, because its charge is minus 2. So atoms can become charged at the microscopic scale. They do so by becoming ions. Molecules can also become charged. I could draw any molecule you want here, and it's certainly possible, and it certainly happens, for that molecule to become charged. Sometimes its natural state, just when it's hydrated in water, is that it becomes charged. Things fall off of it in water. They would rather be in the water than stuck to the molecule, and they become charged. So this is how things become charged on the macroscopic scale. And now we will do macro charge. Macro just meaning large. So in physics, we often talk about a body. So we don't really mean anything specific by body. Body just means a large object made out of matter. That's pretty much all it means. In electrostatics, one of the greatest things to use as a body is Teflon. Teflon has very useful properties, which we'll be showing you very soon. So when I first taught this class, I went back into the demo closet and said, well, I need the Teflon rod to do all the demos. And I was extremely disappointed. This big, beautiful lecture hall with 280 seats and full of students eager to learn about physics. And this is the Teflon rod in Physics 102 at Rice University. This is what I was given to demonstrate electrostatics. I couldn't live without it. So I got in the McMaster catalog and I bought this. This is a Teflon rod. You can really do demos with this. You can really go to town and explain some physics with this Teflon rod. So we will be using this Teflon rod quite a bit in our demonstrations and in our explanations of physics. So our body is simply a Teflon rod, and it weighs 0.37 kilograms. So what's the first thing we want to do? Well, I guess if we want to think about charge in this rod, we simply say how much charge does it have? And you can actually figure that out from what you already know from the micro scale of charge. Because you could say, okay, this thing weighs 0.37 kilograms, and we learned that the mass of charge was very small, 1.7 times 10 to the minus 27 kilograms per nucleon, where a nucleon is either a proton or a neutron. Just if you're talking about one or the other, you call it a nucleon, things that live in the nucleus. So we have our big mass divided by the mass of an individual nucleon, and you put those together and you get 2.2 times 10 to the 26 nucleons. So you actually don't need to know the chemistry of this thing or even what atoms are in it. If we know that it weighs 0.37 kilograms, we know that that mass is almost all in the protons and neutrons. The electrons don't weigh much. Then we can actually estimate the number of nucleons in this thing. Now, another thing we need to know about atoms is that there's usually roughly equal numbers of of protons and neutrons in the nucleus. It's almost never exactly equal, but it's usually very close. With lithium, it was 3 and 4, and it's usually closer than that. So if that's true, then we know that roughly half of the nucleons are protons. So we know we have 1.1 times 10 to the 26 protons. Okay? And if that's true, now we can figure out the charge because each one has a charge of 1.6 times 10 to the minus 19 coulombs per proton. Okay? So if you multiply those two, you end up with 18 times 10 to the 6 coulombs. That's 18 million coulombs. There are 18 million coulombs of positive charge in this macroscopic Teflon rod. Now, if I were really holding 18 millions of coulombs of charge. It would be the greatest demonstration you've ever seen in your life. It would blow you away. I mean, it would literally blow us all away. Out of the room, building would be gone. Okay? But we survived this demo. We aren't all, well, I guess only I and the cameraman would be blown away because this is a distance thing. But we survive because there's not just 18 million coulombs of positive charge. There's also 18 million coulombs of negative charge. This is the difference between microscopic and macroscopic. So in addition to all the protons, there's electrons, and they're so mixed together, so tightly, that we don't see the charge in the macroscopic world. So it does have 18 million coulombs of protons, and it does have 18 million coulombs of electrons. But when you put them together, you get something that macroscopically just appears neutral. And this is how you have to keep in mind about macroscopic objects. When we say they're neutral, they're actually still fairly exciting. There's still a lot of charge in there. It's just completely mixed together and balanced. So we decided my Teflon rod has 18 million coulombs of charge, but it has both positive and negative charge, and they cover each other up, and it comes out neutral. So now we have to figure out, how do you get a macroscopic object to charge up? And the answer is you charge by rubbing. It doesn't sound very technical, but that's actually how electrostatics got started, is charging things up by rubbing. So what I'm going to do is rub this Teflon rod with this cat pelt. So, unfortunately, one animal did die for the sake of Physics 102X. It was an ugly cat, though, so nobody really cared. And as I rub it, we're going to have 3 lines of evidence that something is happening. Okay? The first is sound. As I rub this, you can actually hear sort of a crackling sound. Let me hold it close to my mic. It kind of crackles. Right? So you got a sound. For the second, I'm going to have Alex come. Alex has been helping me with the class, working on some of those 3D visualizations. Hello. And I'm going to have him hold out his bare arm, and I'm going to bring the charge rod near his arm. And what does that feel like?
It feels really tingly.
Tingly. Excellent. Exactly what it's supposed to feel like. Tingly, thanks. That feeling is called formication. That's F-O-R-M-I-C-A-T-I-O-N. That's a medical term for a tingling sensation. So you always feel that near a charged object. So there we go. We got sound. We have formication. A third effect that you can see with a charged object is I'll take these pith balls. These are little really light balls that have been colored to look nice, and they tend to get charged up. And if I bring the Teflon rod charged near the pith balls, you can see as I move it across, they start to move and they fly around under the influence of the charged rod. So there you have something begin to move. It felt a force. It has mass. It went from 0 velocity to some higher velocity, so we applied a force. So that's 3 things going on. So clearly something is happening with this rod when I rub it with a fur. So let's look and see if we can figure out what's going on. Well, at first, the Teflon was neutral. So if we were to zoom in on its surface really hard, we would see atoms, little nuclei here, and they would have electrons going around them. So we'd have positive and negative charge. It's right on top of itself. So this is how it's neutral. And if we were to take the fur over here, same story. If we were to zoom in on it, the surface of the fur, really hard, there'd be little fur atoms. I mean, they're not really fur atoms, but you know what I mean. And they would have positive nuclei, negative electrons going around. Everything is neutral. But let's think, what would happen? What happens when we rub something? You might think these are chemical bonds. I mean, nothing's going to happen when you just rub. What you got to remember is when you rub, you're taking the energy from your macroscopic muscles and you're putting it only in these surface atoms. That's a lot of energy you're dumping into that surface. It's definitely enough to strip off atoms. Okay? Or, I'm sorry, to strip off electrons. So electrons get loose, and what happens is you end up with more electrons tend to go to the Teflon, and more electrons tend to leave the fur. So what I can do is redraw this row. The nuclei are still there, but now it's sort of deficient in electrons, like that. So if we transfer some charge, now the balance is not neutral. Now the Teflon comes out negative, and the fur comes out positive. That's what's going on at a microscopic scale. This is called the triboelectric effect. And unfortunately, it's very complicated. You can't just calculate how much charge is going to transfer. in a triboelectric experiment. It depends on the exact surface chemistry, the previous surface treatment, and the previous surface chemistry. It depends on the humidity in the air, what kind of gas is in the air, how hard you rub, how fast you rub, what kind of fur it is. It depends on a lot of things. It's not really an exact science. However, people have been studying it for centuries, and what you do to study it is you make a table. So this is called a triboelectric series. It's a list of materials, and at the top are materials that tend to come out positive, and at the bottom are materials that tend to come out negative. So if you rub two materials on a triboelectric series, wherever they are on the table tells you what happens. You know, if we rubbed cat fur and Teflon, so Teflon's at the bottom, it came out negative, cat fur is at the top, it came out positive. The lists are always kind of weird. There's always different kinds of fur, and rabbit's always above cat, and nobody knows what's going on. But some aspects of it you can actually understand in terms of chemistry. So think back to chemistry. One of the first things you learn in chemistry is electronegativity. That's basically how much does each atom want to hold on to electrons and grab electrons. It's a function of their atomic and electronic structure. And you may remember from that table, or from that periodic table, you know, labeled for electronegativity, that fluorine was one of the most electronegative elements. It turns out Teflon has a lot of fluorine on it. Teflon is basically plastic where all the hydrogens have been replaced with fluorine atoms. So chemically it actually makes sense that Teflon's way at the bottom. It loves to grab atoms, or it loves to grab electrons. Always ends up negative. That's why I use it in the demonstration. So charging things by rubbing doesn't sound too technical, but it's definitely the way we get started in electrostatics.